Hello everyone. In this new video, leading towards the calculation of areas, we're going to discuss Riemann sums. The basic concept behind Riemann sums was to estimate the area that lies between a continuous curve and the x-axis. At first, we did not have access to very sophisticated methods. With time, successive improvements were made using notions that were themselves already discovered. In fact, Riemann's first estimations used rectangles and eventually limits to approximate the area above the x-axis and below the continuous function y equals f of x, while remaining within the bounds a to b. This approach will have imperfections, but it's certainly a step in the right direction. So consider this curve where points on the curve respect the equation y equals f of x, and consider the interval a to b. One approach that was taken by Riemann was to simply squeeze in rectangles that were contained between the x-axis and the curve itself. So this is very basic, and of course you can tell that there will be approximation errors simply because in this example, all the rectangles, although they touch the curve at one of their extremities, are below the curve themselves and therefore underestimate the area that is there. So that was the basic idea. So can you tell the characteristics of each rectangle that will have an effect on the ensuing estimation? There are a few things, I guess. How do we determine the height of the rectangles? How do we choose their width? Because that will have an effect on each rectangle's area as well. And how many rectangles do we wish to use? All of these are excellent questions that will require that we pause, think, and find up or come up with some kind of response. So let's go through an example first, which will allow us to have something a little bit more tangible and numerical to handle. So let's consider the area that's bounded between the parabola minus x squared plus 6x plus 1 and the x-axis within the interval 0 to 4. So here's a graph of the function that you see in red, and in our first approximation, I've chosen to use 4 rectangles. The 4 rectangles themselves have equal width, so all of the widths are 1. And arbitrarily, I've decided to make my rectangle's height correspond to the function's value at the left-hand side of each bound. So for instance, in the interval 0 to 1, the function's value at 0 determined the height of my rectangle. In the intervals 1 to 2, the function's height at 1 determined the height of the rectangle, and so forth. You'll notice that there are pretty big underestimations taking place in the first 3 rectangles, and there is a slight overestimation taking place in the last rectangle. Here's the kind of drawing you would get if you went to a more sophisticated approach where 8 rectangles are used. I'm still using the left-hand points of each subinterval to determine the height, and this time the underestimations are less than they were before. Now imagine if I had used another subdivision. Here we have 16 rectangles, and you can tell that the errors of estimation are diminishing throughout the process. So this would have been a better estimation of the area under the red curve. Someone else might have decided that a better approach would be to use the right-hand point of each rectangle, or the right-hand point of each subinterval, to determine the height of the rectangle. So in this right-hand picture, notice how the first rectangle's height corresponds to the right-hand value of the function. So in the interval 0 to 1, the function's value at 1 has determined the height of that first rectangle. The function's height above x equals 2 has determined the height of the second rectangle, and then same for 3 and same for 4. Comparing the two graphs, you'll notice that on the right choosing the right-hand point of each subinterval has overestimated this time the first three rectangles compared to the area under the curve. And we have a slight underestimation of the area if we use the last rectangle. But still, overall, I think we're overestimating. Someone else might suggest to use midpoints. So this time, the midpoint of each subinterval was used to find the function's height and correspondingly the rectangle's height. The advantage of this method in the current example is that we are underestimating on one half of the area and overestimating on the other half. So it looks like there's a compensation, and perhaps this would be the most accurate of the three approximations we're doing. But keep in mind, all of these are still prone to error. So here are the three approaches that we've discussed. In the first picture, left-hand points of each subinterval are being used to determine the height of the rectangles. In the second graph, the right-hand point of each subinterval and the corresponding function's value determines the height of the rectangles. And finally, in the last, there are the midpoints that determine the heights of rectangles. Now, no matter what approach you use, going from 4 rectangles to 8, and perhaps even eventually to 16 rectangles, will improve the accuracy of the areas. So how do we choose the width of the rectangles? Well, actually, it's arbitrary, but for convenience, we typically use rectangles of equal width, such as those I've done in the previous examples. How do we determine the height of the rectangles that will approximate the area? Well, the height corresponds to the function's value above a point that we choose arbitrarily within a subinterval. In the examples we've done in the previous slides, I've used systematically either the left or the middle or the right-hand point of each subinterval, but there is no strict policy on that. You could pick any point within each of the subintervals to do your approximations. How many rectangles do we wish to use? Well, that's also arbitrary, but it will definitely have an impact on your estimation errors. As we've seen, more rectangles typically lead to smaller approximation errors. In terms of notation, let's assume for now that the function f of x is positive, or at least non-negative, over the interval a to b, and that we choose to estimate the area between f of x and the x-axis using n rectangles. Then delta x is the notation we'll use to represent the width of each subinterval, which we find by measuring b minus a, so the width of the total interval, divided by n, so the number of subdivisions. This will also be the base of each rectangle and will be involved in the calculation of area. The subintervals will then range from a to a plus 1 delta x, that will be the first subinterval, and then from a plus delta x to a plus 2 delta x will be the second subinterval, and so forth. We use xk to represent the arbitrary point that we will choose within each of these intervals. So for the first subinterval, x1 is the choice we're going to make. For the second, x2, xk would be for the kth subinterval. As for f of xk, this will be the notation we'll use to represent the function's value for the x value we've chosen within each of the subintervals. F of xk is the height of the function above the chosen point. It will also act as the height of our kth rectangle. So for instance, if we choose to have n subdivisions, here is what our area will look like. F at x1 will be the height of the function, but also the height of the rectangle. Delta x will be its width, and so forth for the second. So the total area can be approximated by the sum of the rectangle's areas. And that's why we have a sigma notation here. K equals 1 to n represents the first, second, third, and nth rectangle. F of xk is the height, delta x is the width, so we're adding the heights of n rectangles. For example, let's estimate the area between the parabola minus x squared plus 6x plus 1 and the x-axis within the interval 0 to 4 using 4 rectangles. And at first we're going to use left-hand points from each subinterval. So delta x would be 4 minus 0 over 4, which is 1. This is the width of the interval divided by the number of subdivisions, so 1. The subintervals are therefore 0 to 1, 1 to 2, 2 to 3, 3 to 4. They will act as the base of each rectangle. So in the first interval, 0 is the left-hand bound, and the function's value is 1. In the second subinterval, 1 is the left-hand bound, and the function's value above this point is 6. The third subinterval's left-hand point is 2, and the function's value is 9. And finally, in the fourth subinterval, 3 is the left-hand bound of the subinterval, and the function's value is 10. So graphically, here's what we've got. We've got our 4 subdivisions, and we calculated the function's values at each left-hand point of the subinterval to act as the height of the rectangles themselves. The base being 1, we're ready to add up our areas. So here we go. Here is the addition of the area of the 4 rectangles we have. So we would have 26 as an estimated value for the area under the curve. Granted, this will be an underestimation of the true area under the curve. As you can tell, we're making errors that tend to be more underestimations than overestimations. Okay. Same example, but this time using right-hand points, just to show the contrast. So the width of the subintervals will remain equal to 1. The subintervals themselves are the same as they were before. The only difference being the choices we are making now are to pick the right-hand point within each subinterval. So 1, 2, 3, and 4 are the right-hand points of each subinterval. Above those points, the function's value is 6 and 9 and 10 and 9. So again, this time we're taking right-hand points where the function's values determine the height of the rectangles. And with bases of width 1, we're ready to add up all of the areas, which will this time give 34. So we've got 2 pretty different estimations. I think this last one would be an overestimation according to our picture. I'll bring you back just to show you. Our rectangles seem to be more prone to be over the actual curve than under. So probably the number 34 is a bit of an overestimate. Again, just to highlight the differences that we might encounter, if we wish to have a slightly more precise estimation, perhaps using 8 rectangles would be a better idea. I'm going to do this next example with right-hand points. So this time, using 8 subintervals means the width of each rectangle will be 0.5. The subintervals of size 0.5 subdivide the interval 0 to 4 into 8 segments. I've built a list here where under xk I've listed all of the values that constitute the right-hand points of each of the subintervals. So 0.5 is the right-hand point of the first subinterval, 1 is the right-hand point of the second, and I have calculated the function's value corresponding to each of these points by substituting each of the xk into the function's expression. So we're set, we have the functions and therefore the rectangle's height, and we know the width of the rectangles is 0.5. So what I've done is I've done the summation of all of these multiplications, and the end result is 32.5. So 32.5 is the estimated area. Here is a picture of what we have just calculated, and you'll agree it's a slightly better approximation than what we had previously with 4 rectangles.